lots of time on in Algebra 2. Some of them we just kind of briefly mentioned and we didn't really do a whole lot with. So we kind of have both ends of the spectrum there. With these functions, when I talk about them, we are also going to list a lot of properties that go along with them. And I want to be clear on what I actually expect of you guys. I don't want you to just sit down and memorize that the identity function has a domain this and a range this and it's continuous here. What I expect is if I give you the function, you should be able to draw the graph. And then you should be able to look at the graph and tell me the domain, the range, and those questions by looking at the graph. Okay, and that part we have done before. Okay, so first thing on here, I have a definition. We are talking about continuous functions today, so we have to know what it means to be continuous. And the most basic definition, if we just kind of dumb it down to its very simplest idea, it basically means that you can draw the graph without picking up your pencil. And that's what it means to be continuous. So if you have to stop and pick up your pencil anywhere, we call that a discontinuity in our graph. Anywhere it's not continuous, it is discontinuous. So for example, this is a nice continuous function because I could draw that whole thing without picking up my pencil. But if I had this, a line with a hole in the middle, I would have to stop and pick up my pencil when I got to that hole in my line. So it is not continuous everywhere. It's continuous everywhere except that single point. Does that make sense to everybody? I know what continuous means. Like we've been doing, when I ask you where things are continuous, I am going to expect intervals. You will use the x values when you list the intervals. The only time you should be giving me y values is if I ask for the range of the graph. So I want to look at each of these and decide the intervals of continuity. So we're going to do an interval using x values that gives where this function is continuous. If I look at this first one, it is really hard to tell on your graphs because it hit my tick mark, but there is an open circle on this right here at 2. That is open. So where is this function not continuous? Answer that question first. It is not continuous at 2. So that means it is continuous. If I ask for that interval, what would it be? Negative infinity, comma. Now careful, I want the x value. What's the x value? 0. Union 0, comma, infinity. So even though it's very easy to look at it and state that y, you have to give me the x. The reason being, this same graph can hit a y value more than once. You know, y equals 0 on this graph twice. But since it's a function, the x is unique. You only have that value one time. B, where is that one continuous? Do you have to pick up your pencil to draw it? No, so it's continuous the entire time, negative infinity to positive infinity. C, where would this one be continuous? Everywhere except 2. So negative infinity to 2, union 2 infinity. And D, where is that continuous? There's no open circles, it's continuous everywhere, so we would just say negative infinity to positive infinity. Do we have questions about called a union. It's basically like an OR. So you are continuous from here, from negative infinity to 2. We have to stop at 2. So if you have more than one piece, we just always put that U between them. And then it's continuous again after 2, from 2 on. And we make sure we put the parentheses on our 2, so that means not equal to 2. Yes? Yeah. Anything else? I might also ask you where a graph is increasing, decreasing, or constant. Increasing, we're just talking about left to right. So increasing means our function is rising from left to right. So something like that. That is increasing. Decreasing would be it's falling from left to right. And constant would be no change. What would that look like? Horizontal line. You have to be really careful. If I put something like this, people always tell me it's increasing because the arrow's going up. Okay, I'm not asking which way the arrow's pointing though. I'm saying if I were to graph going from left to right, this is still falling as I go from left to right. So the direction matters there. You don't just look which end of the arrow is pointing to. Again, just like with continuity, we always list the x values when we do that. So what we're going to do now is get into all of the basic functions that we are going to look at. So we've got 6 of them today. And I'm going to ask a series of questions after we graph each of these things. So our first basic function is the identity. F of x equals x. We should know how to graph that. What's that equation? Yeah, it's just like y equals x. That's a line, y-intercept of 0, slope of 1. So we can graph that. Start at 0. Slope is 1, so up 1 over 1. You can put more points if you need to. I'm really bad at drawing straight lines up here, so bear with me. So that is my identity. So, questions about this? Domain and range. Those are things that I would have asked you on the last test. What would be the domain of that function? Negative infinity to positive infinity. What's the range? Same thing, yeah. Because you have one end that's going down forever and one end that's going up forever. Okay, increasing, decreasing, constant. As I go from left to right, what is this graph doing? Increasing the entire time. So it's increasing from negative infinity to positive infinity. So no decreasing, no constant. Continuities, where is this graph continuous? The whole way. We don't have any breaks in the graph. So it's continuous from negative infinity to positive infinity. Well, that was interesting. Let's put infinities there. Questions there? Look at the next one. This is one that you spent a lot of time on in algebra 2. The square function. What does that look like? I heard somebody say it. It's a parabola, right? We know with this, if I wanted you to graph it, you have to have some exact points on there. So let's go through do a t-chart, I'm just going to kind of do a t-chart out loud. 0 squared is 0. 1 squared, this 1. 2 squared, 3 squared, negative 1 squared, negative 2 squared, negative 3 squared, I don't know why I just made that dash. So that is our square function. When I ask you guys to graph these things on homework or tests and quizzes, I am going to always expect a minimum of 3 exact points on your graph. So I don't just want you to put your vertex at 0, 0 and then slot something down. I am going to be checking that you have at least 3 points in the correct spot. Alright, domain. What x values does this one hit? Right. As we keep going, it's just going to get wider and wider, so it will hit everything. Range. What y values does that hit? Starting at 0 and then going up. Bracket or parenthesis at 0? Bracket, because it does touch the 0. Then it goes up forever. Okay, increasing, decreasing, constant. Let's go left to right. What is this first section of my graph doing? Decreasing. We list the x values. So this side is coming from where? Negative infinity, comma, where does this stop decreasing? 0. Okay. At 0, what happens? Increases from 0 to infinite. Is this graph ever constant? No. Alright, where is it continuous? The whole time, right? So just negative infinity, positive infinity. Again, notice the only time you use y values is when you talk about the range. Everything else is an x value. Questions there? Why don't you guys try to make a t-chart to graph this next one? 0 cubed is 1 cubed. What's 2 to the third? Negative 1 to the third. Negative 2 to the third. So it looks something like that. The chair function. You remember talking about that a little bit in Algebra 2? We didn't use this one a ton, but we did see it a few times. What's the domain of that? Yeah, as we keep going, it will eventually hit every x value. Range. Same thing, because we've got one end going up and the other is going down. Okay, as I go from left to right, what is this function doing? Increasing. Left to right, it is going up the entire time. So this is increasing. Is it ever decreasing? No. Ever constant? No. Where is it continuous? Continuous the whole time. Okay. Yes, ma'am. When you have what? Yes. Unless you have like a piecewise function where you have break in your graph in the middle, but all of these that we're talking about right now, they're all continuous, because there's no breaks in them. Okay. This is our square root root function. So, can you put any number into a square root? No, we can't do the square root of what kind of numbers? Which that are not. Okay, we can do them, but they're not pretty. So we would prefer perfect squares, right? What else? You can't do the square root of a negative, can you? It gives you an imaginary number. So if I start with 0, square root of 0 would be square root of 1 is 1. Would the square root of 2 be nice? So what would be another nice one? 4. Square root of 4 would be 2. One more nice one? 9. Square root of 9 would be 3. And we said we can't do the negatives. So this graph only extends in one direction. All right. Domain. Bracket 0, comma, infinity. Range. As we go from the bottom up, the lowest y value is at 0, and it keeps going up forever. So that's infinity. It's the graph as I go from left to right, increasing, decreasing, or constant. Increasing the whole time. No, it's going to start slowing down, but it is still going to gradually rise. All right, where is this graph continuous? From 0 to infinity. Okay. Let's get another one then. The cube root function. So, can you do the cube roots of negative numbers? Yes. We can do odd roots of negative numbers. So we can put anything into this. Of course, we would prefer perfect cubes. That'll make our life a lot easier. So if I start with 0, the cube root of 0 would be 0. Cube root of 1. Cube root of 2. Can we do that? Is it pretty? No, we could do it, but it's not nice. What would be one we could do the cube root of? 8. 8 would give us 2. All right, negatives. Cube root of negative 1. Negative 1. Cube root of negative 8. Negative 2. What's wrong?
It was so loud. I was surprised sometimes. I was
Fun.
I said, did she just pick up her pen?
All right, so domain of this? Range? Same thing. Okay, as I go from left to right, is this graph increasing, decreasing, or constant? Increasing the whole time. Okay, where's this graph continuous? The whole time.
I don't see it all the time. I see it like there has to be a point at which it's like it will for a little bit,
if you think about if you keep putting these numbers in your calculator, though, it's going to give you a decimal answer, and it'll gradually get bigger. So even though, like in terms of our graphs, you know, they start to look a little flat, if you were using a calculator and getting the exact answer, it's gradually rising. All right. There's one more. Absolute value. This is one you guys talked about a lot last year. So I'm going to give you a chance. I want you to graph it. Just make sure number's positive. So absolute value of 0 would be 1, 2, 3, negative 1, negative 2, negative 3. Okay. So we get our nice, oh, that's where it hit. Close enough, right? Okay, so I get my V. Domain? Range?
Oh, just kidding. No. Wait, 0. 0.
Yeah. Do we hit any negative values? No, we just start at 0 and go up. So bracket 0, comma infinity.
I was wrong.
Okay. So this first section of my graph, what is it doing? Decreasing from negative infinity until 0. The next section of the graph, so this section is falling. As you go, you have to go left to right, yeah. This section as I go from left to right is rising. No constant again, and this graph is it, where is it continuous? All of it. Good. No, just keep your confidence. All right. So far, so good? All right, let's do this one. So x equals y squared. I kind of switched that up a little on you. If we wanted to make a t-chart, which variable would it be easier to plug in values for? Probably the y. Normally we plug them in for x. But since the formula says you are going to do y squared, wouldn't it probably be easier to do the y on this one? Okay, so let's put in some negatives and some positives and 0. All right. So what is negative 2 squared? Negative 1 squared? 0 squared? 1 squared? 2 squared? Oh, that's, excuse me, that is not a straight line. Okay, so if I'm going to graph that, I've got 4, negative 2, 1, negative 1, 0, 0, 1, 1, 4, 2. What is this? Yeah. It's like a parabola flipped on its side, isn't it? So, is that a function? Why? Yes.
Look at you go.
So fails the vertical line that side is not a function. Typically the increasing, decreasing, constant questions, we only ask about functions. So I wouldn't ask you about that here. Any questions on that? The last thing that I want to talk about on here is symmetry. symmetry a few different ways. A graph can be symmetric to the x-axis, the y-axis, or the origin. If it is symmetric to the y-axis, if you just think about your graph, that means if I fold it on the y-axis, it would overlap itself. So what would be some examples of that? Looking at the functions that we've drawn, which ones would be symmetric to the y? The absolute value one. If you fold it on the y-axis, it overlaps itself. What other one? The square function, x squared, our parabola, would overlap itself. What that means is a positive and negative x give you the same answer. 2 squared and negative 2 squared, both of them equal 4. So if we are checking if our graph is symmetric to the y, what we'll do is put in a negative x and see if we get the same thing back. A graph is symmetric to the x-axis if you plug in a negative y and you get the same thing back. We've done one that would be symmetric to the x, when if I fold it on the x-axis, it would overlap. The one we just did, the x equals y squared, is symmetric to the x. You notice that one wasn't a function, and that will always be true on symmetric to the x. They're not a function, they would fail the vertical line test. So we just plug in a negative y to check that one. Symmetric to the origin means, I have that out of order on my slides. Symmetric to the origin means if you put in a negative x and a negative y, you get the same thing back. For your graph, you have to think about, I'm going to take my graph and I'm going to flip it over the y and the x-axis before it overlaps itself. Look at those graphs. Do you think any of them would match that description? The cube root function, the cubed function, the identity. If you think about the cube function, for instance. If I just flip this thing over the y-axis, it would look like that. And then if I flipped it again over the x-axis, doesn't it overlap the original? Okay. So, we can check symmetry a couple ways. Sometimes we can just look at the graphs. Sometimes we are going to have to look at the equations themselves to check for symmetry. How much time do I have? Okay, let's go ahead. The last thing I put on your handout, because I didn't print everything for you guys, I put the even and odd, so I'm going to go ahead and go over that definition because it's on this handout that I printed for you. Even and odd is related to symmetry. Even is the same thing as symmetric to the y-axis. So if you put in a negative for your x or a positive for your x, you get the same thing. Okay. Typically when we look at even and odd, it's written in function notation, so that's why I had the s of x instead of the y here. Odd is the same as symmetric to the origin. So negative x and negative y do the same thing. We already said if it's symmetric to the x-axis, is it a function? No. So when we're talking about even and odd, we won't see any of those. Okay, I think I'm going to go ahead and stop here. I will do the examples over even and odd and symmetry tomorrow in class. I went ahead and opened the Math Excel assignment for this section. It's open now, but it is not, let's see, today's Tuesday, so it will not be due until the end of the day, Thursday. We're not done with the section yet, we're working on it tomorrow. Now, there are a couple things I want to mention about this Math Excel. You do have to watch your directions. It's going to give you lots of graphs and ask you, is it increasing, decreasing, constant? You have to give interval notation for the increasing, decreasing, constant. On Math Excel, they only use open parentheses. Okay, let me show you what I mean by that. So if I gave you, let's say, this function. This first section of the graph is doing what? decreasing. And it's coming from negative infinity until we get to negative 1. So you can put, when we've talked about it, we've been putting brackets there because it is a closed circle. This is one of those things that math textbooks kind of differ on, because it really doesn't matter if the negative 1 gets a bracket or a parenthesis. Because at that point you're not going up or down. The Math Excel, under each question of those, it says give an open interval. They want you to put a parenthesis on everything for the increasing, decreasing, constant only. So you would say you are constant from where? And it will say give an open interval, so you use parentheses. Increasing where? And it'll say open interval, so just use parentheses. So the only piece you do that on is increasing, decreasing, constant.